I will begin with a word of prayer. Dearly Father, we thank you for this day. Again, I thank you for these students. Just ask that you bless our work this morning. Help us to glorify you, what we do. And we just thank you for this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so we have talked about vectors, right? And so there's a lot to say about vectors. I'll just remind you the high points. Every vector A can be written as A times A hat. That's a lie. Why is that a lie? Not true for the zero vector, right? But any non-zero vector can be written as a magnitude times a direction. And then we have learned that we have two basic vector operations. Well, maybe there's three, all right? Maybe there's really three basic vector operations, right? What's the third and more basic vector operations? The first thing I talked about, actually. Vector addition, right. So, I mean, we kind of take that for granted, but that's another thing, right? So, A dot B is A1 B1 plus A2 B2 plus A3 B3. That's the dot product. The cross product was A2 B3 minus A3 B2, comma, A3 B1 minus A1 B3, comma, A1 B2 minus A2 B1. Of course, you can also calculate that thing with the determinant mnemonic, or the circle of cross products, and just hand-to-hand combat with x hat, I hat, y hat notation. A plus B is, well, let me just write it this way because this is better. The jth component of this is equal to the jth component of A plus the jth component of B. I guess there's a fourth, right? Because we had, that does let us not forget, scalar multiplication is a thing. So, you know, each of these plays a part. Now, far less trivially is the fact that these top two have slick formulas that relate to the angle between the vectors, right? So if I have vector A and if I have vector B, I've got angle theta here, right? This is the length of B, the length of A. And the dot product is AB cosine theta. Let me emphasize again, the dot product is a number. If you write dot product as a vector, I will take off a lot of credit so that you remember not to do it again, right? Maybe I should institute negative partial credit for that. I've been itching to try this somewhere. Do you guys know about negative partial credit? The idea is it's an error so bad that I can take off points from other assignments. No? No? Like in a theology class, like you violate the doctrine of the Trinity. Ooh, sorry, failed the course. You know, something like that. No? No? Okay, all right. And then this one, I essentially motivated it by this. AB sine theta is the magnitude. And then n hat, given by the right-hand rule. Right-hand rule. That's RHR, right-hand rule. Now, let's see here. Now, let me just give you some pictures about the right-hand rule. All right, so if I have A is this way, right? And if I have B is this way, right? Take my right hand, I point it in the direction of A, I cross into B, my thumb points out of the board. Now what kind of, we need some kind of easier symbol for that, because drawing in perspective is really kind of a drag. So a lot of people, the convention they use is something like this, a circle with a dot. And the idea of that is it's like an arrow pointing out of the board at you. So the arrow you have to kind of imagine as one of these deals. I don't know if anybody really has an arrow like this, but you get the idea. Maybe you get the idea. I don't know. I'm trying, guys. I'm trying. So that would be the conical arrow tip, like maybe one of those exploding arrow tips like Rambo had back in the day. Oh, I'm sorry. You've never watched Rambo? It's an R-rated movie. My apologies. No, you watch it on TV. Maybe on VidAngel. Can you watch Rambo on VidAngel? You guys aren't Mormons. Never mind. What? What's that? No? Are Mormons Christians? Something to think about. All right, so on the other hand, if I had A here, I think the question there could be answered is the Mormon Jesus the Jesus that Christians worship? Anyway, so here A, if you want to understand more about that, like look up some YouTube videos by Jeff Durbin, who's on the street, like interviews with Mormon missionaries. They're like really interesting. But anyway, Jeff Durbin, this guy. Anyway, so A crossed B. I saw Dr. Joseph today, so I was inspired to do some kind of moderately theological Thursday, right? So almost. It's a passing comment, but it counts. So A cross B, thumb, yo. Don't do that. So it points into the board, which means if you think about looking at the arrow, what are you going to see? You're going to see the tail fins, right? So the picture for that is simply this. So those are our diagrams for out of the board, into the board, all right? Into board, out of board. Now what more can we say? The other thing, of course, was that if we have x hat, y hat, z hat, we've got this circle of life, circle of cross products, like this, x hat cross y hat is equal to z hat. On the other hand, if you do z hat cross y hat, what do you get? Negative x hat, because we're going against the grain, right, against the order here. So now another thing I should mention, of course, because there are other notations, right? X hat is equal to I hat, which is equal to I tried. What I'm trying to do is a bold-faced I. It doesn't really work, but a lot of times textbooks don't have a hat on the J. They've just got it like a bold J. But in my experience, trying to write a bold J with marker is like really sketchy. Maybe if I had chalk I could do it, I don't know. But just so you know, those are oftentimes notations which are used in other calculus books, but in my notes we use x hat, y hat, z hat. All right, any questions? Just a quick review of where we are. What are the properties of the cross product? That we really have only touched loosely on. Properties of cross product. We talked about the properties of the dot product before, but we haven't talked about the properties of the cross product. So first of all, this is kind of a dumb one, but A cross B is a vector. That's important. Unlike the dot product, it's a vector, right? It's a vector. What is the meaning of the vector? What is it? Like, if you had to put in words, what is A cross B? It is the vector perpendicular to both A and B whose magnitude is, area of that, right? The magnitude is the area of the parallelogram which has sides A and B. That's what the cross product is. And that's not quite Unique, what else is it? With the direction specified by what? Right-hand rule. Right, the direction is specified by the right-hand rule. I think this marker is, this lives a good life. Whoa! Cool. What did I hit over there? You're gonna try? All right. I should warn you, once you start, it's hard to stop. Okay, so great. So this is just basically definition, right? Now here's more interesting ones. A cross B is equal to minus B cross A. If we have a sum of two vectors, A plus B cross C, we have the distributive property, A cross C plus B cross C, right? And also, if we have like A cross, let's say, a constant times B, that's the constant times A cross B, right? So these are sort of entry-level properties of the cross product, all right? Other thing to know about cross product, not associative. So there's that. A deeper property of the cross product is the cyclicity of the cross product, which is this. A dot B cross C is equal to B dot C cross A is equal to, can you guys, do you know what I'm talking about, this cyclicity, this pattern? Basically the idea is you take the symbols, right, and push them this way. And as you push it this way, this one drops off the edge and comes back to the other side. So think about pushing the letters over where the first becomes the last. And they just, it's kind of like people moving up in line. So now I go to C dot A cross B. So this is called cyclicity of the cross. Now this is not the cross product, right? What is this? This has a name also. Yeah, this is the triple product, which isn't really a triple product, except that it's what? It's got three things in it. That's why it's a triple product, right? So what is the significance of the triple product? One thing is, there's a formula for this. You can write this as the determinant of A, B, C, if you like that. Well, I mean, you can either put A, B, C as column vectors, or you could put A, B, C as row vectors. Either way, the determinant is the same, whether you look at the matrix or its transpose. If you don't know what a matrix is, if you don't know what a transpose is, don't worry, you'll see it in 221 soon enough, all right? So, for an example of that, I'll keep it really easy. A equals to 1, 2, 3. B, this is not really easy actually. Okay, I'll reform. 0, 1, 0, and C equals to 0, 0, 1. Fine. What's A cross B in this case? So we've got, I'm going to do it in the x hat the x hat notation. So I've got x hat plus 2y hat plus 3z hat, and I'm taking the cross product with B, which is what? Just y hat, right? Now we can calculate this. Yep. Oh no. Okay. We can calculate this cross product. X hat cross y hat is what? Z hat, right? What's y hat cross y hat? Just 1. Oh, no. Check this out. So one of the things I seem to have buried the lead here. I should have taken a second when I got to here to go, oh, wait a minute, what happens if we put A equals to B? If we get A cross A is equal to minus A cross A, right? That tells me what? That tells me twice A cross A is equal to 0. What does it mean if twice a vector is 0? Well, yeah, it's the 0 vector, right? So any vector cross itself is 0. So y hat cross y hat is just 0. So this, when this crosses with that, we just get 0, right? And what's z hat cross y hat? Well, negative x, so I get minus 3x hat. Lo and behold, we've got the vector minus 3, 0, 1. That's the cross product of A and B here. Now what happens if we calculate the triple product A dot B? A cross B dot C. Oh, I seem to have put the dot product. Fine. I'm trying to stick with the pattern I had down here. My bad. Poor planning on my part. I should have taken the cross product for like B and C if I was going to do that one. Oh well. It doesn't matter because I just said this is true. So what's C dot A cross B? In other words, we've got 0, 0, 1 dot product with minus 3, 0, 1. We calculate dot product, x times x plus y times y plus z times z, talking about components. So you get what? 0, 0, and then, so you get 0 plus 0 plus 1. So it's just 1. The triple product here is 1. And if you were to calculate the determinant of 1, 2, 3, 0, 1, 0, 0, 0, 1, you would also get 1. Right? To calculate that determinant, you follow the same pattern I did last time, but instead of having the x hat, y hat, z hat outside the 2 by 2 determinants, you just put the numbers for, So basically, the way this would be calculated is 1 times the determinant of this stuff. And then minus 0 times the determinant of 2, 3, 0, 1. I'm trying not to burn too much class time on this because you guys are going to cover this in 221 anyway. But this is so-called Laplace's expansion by minors. They'll probably use this to define the determinant in the 221 class. Anyway, so these are obviously 0, and this gives me 1 times 1, which is 1 as I claimed, all right? Now, there's a formula for the determinant of a 3 by 3 matrix. I'll just mention this in passing. If I wanted a formula for this, it's actually equal to the sum I, j, k of epsilon I, j, k, ai, bj, ck, which is exactly equal to the sum over k of ck times the sum over I and j of epsilon I, j, k, ai, bj. But you see, this right here is the kth component of A cross B, and this overall is the formula for C dotted with A cross B. This calculation I just did is the bonus part of the course. That's the difference between an A and A plus, understanding that. If everything I'm doing right now is hieroglyphics, like, it's okay. Don't feel bad. It's more important, of course, that you understand, like, example 1. But this is the kind of notation I use to prove things in here. And I'm just telling you, this notation has vast benefits. It's the start of what's called Einstein notation, right? If you want to understand like the equations of general relativity, right? Gravity in curved space. Wait, any flat earthers? Okay. Personally, I believe in the cylindrical Earth, but anyway, that's a long story. So, and a joke. But just to be clear, C dot A cross B is the triple product. As you can see, it's the determinant. See, this symbol right here is it's this completely anti-symmetric symbol. It builds in those 6 terms, 3 pluses, 3 minuses, and that's what's needed to define the 3 by 3 determinant and also the cross product. It's really the same math. Now, well, this calculation I just did is the kind of calculation that I'm hinting at the end of mission 1, that last bonus problem. It's that kind of calculation. And there's more of these you'll find in the posted homework. If you want to see more, just ask me about it in an email. I'll point you to them. There's some in the notes, obviously. Geometrically, what does, well, first of all, one other thing. So example 2, what if we had C equal to, oh, I don't know, 1, 2, minus 2. Same A and B. What is C dot A cross B now equal to? Oh, my bad. What am I using this smudger for? All right, fine, I'll content myself with this. Where was I? Minus 3, no, I'm a dummy. It's right there. 1, 2, minus 2, dot product with minus 3, 0, 1. Okay, fine. How does this work out? Minus 3 plus 0 minus 2. The dot product is minus 5. You should be able to check me on that, right? Can you guys explain to me the geometric significance of both of these calculations? Let me draw a picture, if I can. Here it is. I think I'll put the picture over here. So if we think about 3 vectors, right, so we have, let's say, A here, maybe, all right, and then B here, all right, and then maybe C. And so let me just first of all kind of draw another one here like this, and then like that, all right. So this is a parallelogram, right? And then my third vector, my C, let's say it looks like this, all right? I guess I'll put the B, I'll label the B over here so you can kind of tell the difference better. All right, and then I also put a C here, and here, and here, right? And then I should have color coded A and B. Oh well, too late. This is A, another A up here, right? And then I put some more B's. It's not too late. Color coded. There we go. Here's my B's. Like that. What's this giving you? What's this giving you? It's giving you like a 3-dimensional cube, like a slanted cube kind of thing, right? This slanted cube kind of thing with parallel sides is called a parallelepiped. Parallelepiped. What a stupid name. Parallelepiped. I'm probably misspelling that. My apologies. The thing is, you know the area of this down here, right? What is it? It's AB, whatever this angle is, sine theta, right? And that's, of course, the dot. That's the magnitude of the cross product, right? how do you figure out the volume of a parallelepiped? Now, if these purple lines, if the purple lines were just, straight up from A and B, it'd be easy. You just multiply by the length of C, right? But what if the purple ones are like super tilted? Then the volume wouldn't just be the area of the parallelogram times the length of C. What would it be? Well, there it is. I'm looking for another color, and it's right in front of me. So you have to kind of think about extending this, right? And you'd want the, I don't know if you're, this is supposed to be right angle. The point is, you need like the height, right? The height of the one base off the other. And to draw it more specifically here, well, I'm never successful in drawing this picture in class. I don't know. Every time I try to draw this picture in class, something bad happens. I regret it. So here's a picture of the parallelogram, all right? Let's take a 2D perspective. And then here's a picture of C, all right? From the side. What is perpendicular to the face of the parallelogram in the vectors? What vector is that? The what? It would be orthogonal to it, but how do you, yes, it's orthogonal to it. If I was to write A cross B equals to AB sine theta n hat, it's that vector, that one, right? The vector given by the right-hand rule. So if I was to look at this, n hat, looks like that. Of course, it should be a unit vector, so don't make too much of my lengths here. Then, all right, what's this angle here? What's the height then? The height is this distance right here, right? So the height would be what? It would be, if this angle here is, let's say, alpha, it would be what? It would be C cosine alpha, right? That would be the height. But what happens when you calculate A cross B dot C? What do you get? You get AB sine theta times n hat dot C, which is what? AB sine theta, where's my formula? Times C cosine alpha, right? Which is exactly the volume of the parallelepiped, right? Yes?
Could you use the other angle instead of alpha, use the interior angle, and then use the sine of that angle as well?
I suppose you could, but then you wouldn't have, well, the reason I wouldn't want to do that is because the angle interior to n hat and c hat has to do with the dot product of n hat and c hat, which is what I'm trying to get back to. Because what I'm trying to do right now is to derive for you the fact that the triple product gives you the volume of the parallelepiped with edges ABC. Another way to say this, what happens if your triple product is 0? What does that reveal? Yeah, they're coplanar, right? Those three vectors must lie in a plane. Now, that's a lie. Well, this is not a lie, but the thing is, now here both theta and alpha I'm taking to be the angle between vectors, right? So they're angles between what? Between 0, I'll get out of the way, between 0 and 180 degrees, right? Is sine positive between 0 and 180 degrees? What should you be thinking about? The answer is yes. You should just be thinking yes. I'll accept that. So here's a picture of sine, right? Here's a picture of cosine, right? Here's 180 degrees. Here's 180 degrees. So you see this positive, this over here, ooh, that could be negative. Can volumes be negative? They cannot, right? So what we should say, the result of this whole discussion is that the long and short of it here is I'll write it up here, is that the volume of, the parallelepiped with ABC, I guess I need a name for it. For the purpose of my discussion, I'll just call it P. So the volume of this thing, right, is equal to plus or minus A dot B cross C, right? With the plus or minus, we choose the plus or minus so that that quantity is positive. Yeah.
Why would you pick 180? Because it doesn't look like that could go more than 90. That alpha there.
Well, this is just the way I drew the picture. See, in practice, C might be pointing downward. We already saw that over here, in fact. See, when you take a triple product, C dot A cross B, it can be positive, right? Or it can be negative, which corresponds to the idea that if I drew the picture, that, let me draw the picture here. So if I make A go, let's see here, just a second, let me, A here, all right, and then B here, okay, A cross B is, well, I'm going to, I'm not going to do those other pictures. I'm not going to do the these things. That's not. My point to you is here, like C would be kind of like this, right? So you've got this kind of deal, right? Sorry, it's getting worse. On the other hand, over here, are we over there? No, we're over here. Okay. On the other hand, over here, if I have A and I have B, right? C, so A cross B is up here, right? If I think about these two in a plane, right? A cross B is like here. But apparently it's negative, right? What's that mean? That means the C, actually, in the style of my current picture, it's down here somewhere, right? So it actually looks like this. So the answer to your question really is, I drew C as if it was going up, but that begs the question, could it also go down? Well, yeah, and if it did go down, that would correspond to the choice of angle between 90 and 180, which would give that cosine being negative. Now there's a deeper truth here. Well, maybe truth, definition to be had. Definition. If A dot B cross C is greater than 0, then ABC is a right-handed triple. What does that mean? What's a right-handed triple? What I'm saying is that if you think about the plane, all right, so let's see here. Let me find markers that will show up. So if this is my B, right, B, and this is my C. See this? B and C. They lie in a plane, right? So B cross C does what? B cross C is this way for these as I've drawn them on this plane. If A dot B cross C is positive, what does that mean? That means that A is going somewhere. It doesn't have to be perpendicular to this plane, right? But it has to be, it has to know which way is up, right? It has to be somewhere pointing above the plane. Somewhere up here will be positive. This would be the largest it could be in case that A was parallel to the direction of the n hat given by B cross C, if it was parallel. But what's the opposite? It could, the other possibility, of course, is that A is not up here. A is down here, right? In that case, A dot B cross C is going to be what? It's going to be negative. And then three vectors like that, A, B, C, where the third vector is not given in the same direction as the cross product of the first two, well, then those are not a right-handed triple. Those are a an evil left-handed triple, right? So we only use right-handed things because, of course, as we know, since antiquity, the left hand is evil. So I'm just joking. It is our convention to use right-handed triples, right? Sorry, you lefties, but that's what you're stuck with. Now, because of the cyclicity of the trace, you can just as well judge this by B dot, C cross A, or what? C dot A cross B, right? Which, of course, is equal to A cross B dot C, all right? So any of these being greater than 0 makes any of the other ones of them greater than 0. Yes, go for it.
I'm still over here.
Go for it.
If C is supposed to be perpendicular to the parallelogram, why is it at an angle to n triangle?
No, C is not supposed to be perpendicular to the parallelogram. C is just not coplanar to the parallelogram. So like this doesn't have to be. Let the parallelogram be this, all right? So here.
So C in this example is not the cross product?
Here's a parallelogram, right? Like that. The C could be like this, but it doesn't have to. The C could be like that.
Is C the cross product in this, or is it something else?
No, C is the third vector. There are 3 vectors here. A vector, the B vector. The direction of the cross product is given by n hat. So C here would be the magnitude. This C is the magnitude of C. Where did I get the C from? C is the magnitude of the C vector, which is the length of. It's given. I mean, the whole discussion is what's the volume of a parallelepiped? Why is it given by the triple product? That's what I'm trying to get at. But it's okay. I mean, this. I think the picture I have in the notes is better for this one. But anyway. Yeah, I don't know if I understood your question actually, but we can talk about it after class if it's not still gelling. What is it?
Is there a reason you wouldn't use a basic absolute value for that A because C at the top of the volume of that?
Oh yeah. You could just wrap it in absolute value signs. Sure, that would take care of the plus minus. Just to summarize the discussion here, if A, B, and C are a right-handed triple, the triple product gives you the volume of the parallelepiped with edges ABC. If, on the other hand, ABC vector is a left-handed triple, the triple product gives you minus the volume of the parallelepiped with sides ABC. All right, so this left-handed versus right-handed is just it's something we have to face. We try to always make our coordinate systems right-handed. That's why I draw x and y and z in relation as I do. That's why x goes where it does. That's why I always draw. Let's see here. I always draw this, right? X, y, z. That is a right-handed coordinate system. Why is that? Because the unit vectors of the coordinate system are a right-handed triple. The unit vectors of the coordinate system are a right-handed triple. So I've got, this is my x hat vector, right? This is my y hat vector. My z hat vector is like that. In fact, for a right-handed coordinate system, you have to have the cross product of the unit vectors in the first 2 directions gives you the unit vector in the 3rd direction. That's a signature property of a right-handed coordinate system. Now, if this is easier, like what would be the volume of the parallelepiped with edges x hat, y hat, z hat? That's just what? The cube, right? So there, because if you were to, it's just the length of each side is 1, and then all of a sudden we don't need vectors, right? Because we're just like 1, 1, 1, okay, length times width times height, 1. But this whole business we're going through, it deals with the case that the sides are, that it's tilted, right? That you have 3 families of parallel planes that intersect to give you this parallel pipette. What's the volume of such a thing? All right, well, I should go on because the triple product plays a relatively small role in the larger story of this course. But in contrast, what I'm about to tell you about is actually really important. And so that is a line. So let's talk about lines and planes. So we're moving on here, lines and planes. I'm sure I forgot to tell you something about cross products today, right? If you read the notes, you'll see there's a little bit more. Like, as I'm thinking about it right now, I haven't talked about physics, right? What's the typical physics application of the cross product? What's that?
Just moments.
Moments, right. So like if we're talking about applying a force to a lever arm, the cross product of the radial arm with the force gives you the torque applied. And the direction of the cross product actually points in the direction of the axis around which the rotation happens. This is like a good application of the cross product. Or in second semester physics, you use the velocity across the magnetic field. That gives you the direction of the Lorentz force. So there are many places in physics where the cross product comes up whenever there's a kind of perpendicularity to the way the physical interaction happens. All right. So lines. Let's give a definition of a line in here. Listen, you guys can ask me more questions about cross products in future days, of course, but I should move on here. A line through R naught with direction V naught not equal to 0 is parametrized by R of t equals to R naught plus t V naught. So R naught is called the base point. V naught is called the direction vector of the line. Now in Calculus 2, you may have focused on parametric equations to describe parametric curves. Here, we will focus on the concept of a parametrized curve being described by a vector-valued function of time. So let me draw a picture of it, and then I'll give you an equation, some equations for it. But so here, basically, and so I'm drawing this as if it's in 3 dimensions, but truth be told, what I just defined equally well works in n dimensions. All right, you could do that in 4 or 5, whatever. And so here it is. Like there's the line. The base point, maybe it's here. There's R naught, right? And then this is a parametrized line, right? So it has some sense of direction. If V naught is pointing that away, right? If the direction of the curve is like this, you usually draw like a little arrow along these parametrized curves, then what that would mean is that the V naught, you could picture something like this, all right? So let's see here. Let me give you some numbers. What example am I on? 3, 4? What is it? Well, you guys, you pick. What number would you like?
E.
What's that, 3?
E.
E? Okay. I mean, I'll allow it. So it's the base point. There are worse things. I used to have a student who always tried to get me to use 7 as a variable. So annoying. Anyway, 1, 2, 3, because that's like my favorite vector. And then V naught. You pick the direction. What do you guys want the direction to be?
Zero.
0?
7.
0, 1, 7. All right. There was only one wrong answer here, which was 0, 0, 0. right?
That would make the problem really easy.
Right. What happens if you put the direction vector equal to 0 in this formula? What happens with R of t? It's, yeah, R of t is equal to R naught. That is the parameterization of a point. From t equals minus infinity to infinity, R of t equals to R naught. That is just, your parameterization just sits there. Yep, that point. It's just that point, right? So this is more interesting. And the formula is this. R of t equals to 1, 2, 3 plus t times 0, 1, 7. That's a good formula. Now, if you want to collect it, you can collect it. You can collect it together, and you'd have 1, comma, 2 plus t, comma, 3 plus 7t, right? There you go. That is a parameterization of that line, right? Now, perhaps last semester, when you're in Calculus 2, you talked about parametric equations. What would the parametric equations describing the line be here if you wanted to do that? And I usually don't. But if you did, what would they be? X equals to what? Y equals to what? Z equals to what? We're in 3 dimensions. We need 3 equations, yeah? So the x equation is kind of boring. It's 1, right? Y, 2 plus t, right? Yeah. Z, 3 plus 7t, right? So you need to know this, right? You shouldn't have to spend mental energy in the future parameterizing a line. You should ask yourself the question, what's a point on the line? What's its direction? As soon as you know that, you're done. You can write down the equation of it. I should say, not the equation of it, the parameterization of it. What's the difference between an equation and a parameterization? An equation has a relation between x, y, and z expressly. Yeah. I like to think of it as sort of hands-on and hands-off. I mean, I think of the parameterization as hands-on in the sense that you give me a t, I give you a point on the path, right? What if I describe something by an equation? What point is on it? Just looking at the equation doesn't tell you what point's on it, right? You have to like mess around with the equation to figure out where the points that satisfy the equation are, right? So the equation description of a path, it doesn't tell you points on the path directly. A parameterization is essentially instructions, a recipe for constructing the path by essentially gluing a line into 3 dimensions in this case, right? So there's, well, anyway, we'll think more about this as we go on here. I don't have examples yet of the other idea. The other thing I should talk to you about, though, definition. Well, it's not, excuse me, this is not a definition. This is just a, this is a trick. Standard trick. Given P and Q points, the parameterization of the line segment, so let me draw a picture here. Here's my P, here's my Q, oops. All right. What's the formula? And by formula, I mean, what's the parameterization of the line segment that begins at P and terminates at Q? In other words, if I want to say right here is a particular point R of t, what's the formula for that? All right. Here's the standard trick. What you do is you start with P, all right? And then you put t times q minus p. All right, now this is a line segment. The line I didn't specify, but I should have. What does t range over for my definition? If it's a line, it has what? Infinite extent, right? At least that's what we've been saying since like about 2 millennia ago. It's an axiom for Euclid, right? That lines go on and on without stopping, basically. So here t was a real number. It's unbounded. It goes both ways. This is a line segment. It doesn't go on and on. It starts at p, ends at q. So here we're not going to have the parameter ranging from minus infinity to infinity. We just do what? For this formula, all you want, 0 less than t less than 1. Now you guys try it out. What happens when we plug in 0? What do we get? What happens when we plug in 1? What do we get? I mean, try it out. You get what? P plus 0. So you get p, right? What happens when you plug in 1? You get p plus q minus p, also known as q, right? So this is a line segment. You must remember this. If I ask you to parameterize a line segment between 2 points, this is your go-to formula. It's simple. Know it. Don't try to rederive it. Learn this. Although, it would be good if you understood it. What is this? Geometrically, what's going on here? This is just p plus t times what vector? It's the pq vector, isn't it? That we defined last time. What's the direction vector of the line segment? It's a vector in the pq direction, right? You could say that the pq vector is the direction. We also talk about direction for a line, direction vector for a line segment. When we have curves, you guys are itching to get back to calculus, I know. Once we have a curve that moves around in space, the direction vector is going to be given to us by the derivative. The derivative is going to be the direction vector to the tangent line at a point in that curve, but one thing at a time, right? Let's do lines before we do curves. Any questions? Okay. So that brings us to planes. You notice I haven't talked to you about what really is the equation of a line here. These are parametric equations. That's not the equation of a line. The equation of a line here doesn't even make sense. Because in 3 dimensions, a line is one-dimensional, right? What is a one-dimension? One dimension because the parameter tells you the number of parameters you need for an object is its dimension. So a line is one-dimensional because you need one parameter. To describe it as an equation, you'd actually need 2 equations because equations take away dimension. So to describe a curve in 3 dimensions, I need 2 equations to fix a curve. But a plane is what? It's a 2-dimensional thing, right? You could think about laying down a coordinate system in the plane. And I won't start with that because it's a little bit fussier, but if you think about a plane, right? You can think about laying down coordinate lines, right? You've got one direction, another direction. That's a 2-dimensional object. So if we were to parameterize a plane, we would need 2 parameters. But as an equation, we just need 1 equation to describe a plane. So there's a distinction between the equation perspective, which I will sometimes call the implicit perspective, versus the explicit perspective, which is the parametric perspective. So we're going to talk about planes first here. And so here's sort of my generic plane. And let's see here. What should describe a plane? Like what kind of data do we want to describe a plane by, do you guys think? A function? No. I'm going to say no. Sometimes you have to say no. It's hard for me to say no. That's why I always have too much to do. So I guess one way we could describe a plane would be by giving 2 vectors that were in the plane, right? Like That would sort of specify a plane, right? Not entirely. You also have to say, like, you have to at least put one point in the plane so you know where it's based, right? Because these two vectors we could move up and down. It would still be, those would be different planes but the same tangent vectors, right? But on the other hand, if I tell you the vector which is perpendicular to the plane, maybe that's more convenient, because there's just one. Well, that's not true either. There's two choices, but let's try to go with the normal vector to the plane. The normal vector to a plane is the vector which is perpendicular to the face of the plane. Today's Thursday, right? Okay, because if it was like Friday, you guys would have left 5 minutes ago, right? Yeah, okay. Just saying. Okay, so here, this point, let's call this R naught. That's a specific given base point to the plane. We have a point on the plane, all right? And then what else do we get? We also have a normal vector to the plane. Let's call that n. And we'll let A, B, C. That's a typical notation in Calculus 3 for the normal vector, A, B, C, all right? So that is the vector we're going to say is perpendicular to the plane. And R naught is the base point on the plane. So of course we could also say that's x naught, y naught, z naught if we want to be more explicit. Now what would we like to do? We'd like to discover what's the equation for the plane, right? So let's think geometrically. Let's think about an arbitrary point on the plane, which I'll use blue for. Oh, wait a minute, red for. Poor planning on my part. I want to put it over here. This point right here, all right? X, Y, Z. If you like, that's a variable point, all right? R naught and the normal vector, these are fixed. These are given to us. X, Y, Z, this is an arbitrary point on the plane we're trying to characterize. So you guys tell me, if this vector is R naught, right? And this vector here, the red vector, is R, then what's the vector that connects these two things? And shouldn't that be a vector which is in the plane of the plane? I'm using plane to describe plane, sorry. Shouldn't that be a quote-unquote tangent vector to the plane, right? This thing right here, right? What should that be? That should be what? R minus R naught, right? Because if you add the green vector to the black vector, you should get the red vector. See how that works? R naught plus R minus R naught equals to R. Yay. So that vector is tangent to the plane. So what is the relation between n and that displacement vector, R minus R naught? They're orthogonal, right? So we know that n dot R minus R naught is equal to 0. This is the vector equation of a plane. The vector equation of a plane is that, right there. We're looking at it. What does this look like in terms of scalars? Well, check it out. You got A, B, C dotted with x minus x naught, y minus y naught, z minus z naught equals to 0. This is still the vector equation of the plane, although it's starting to get a little dicey as to whether it's still really the vector. I mean, it's a very cluttered vector equation of the plane now. Let's actually work this out. This is what? A times x minus x naught, right? Plus b times y minus y naught plus c times z minus z naught equals to 0. And there you go. That, my friends, is